two balls, my wiffle ball and my tennis ball. The wiffle ball has less mass than the tennis ball, so if I set them both here on the table and push them with the same amount of force, the wiffle ball travels farther. This is because having less mass, it also has less inertia and is going to be less inclined to remain in its unmoving state. Inertia is given by something called the Higgs field. It's a field that permeates our universe, and it gives particles their inertial mass based on how much they interact with this field. It works sort of like a fish swimming through water as compared to an elephant. The fish is going to be more hydrodynamic and interact with the water less, means we will travel farther and faster than our elephant. This is sort of like how particles interacting with the Higgs field works. Particles interact more with the Higgs field, are going to get more inertial mass, and they're not going to be able to travel as far as particles interact less. This is important because in the history of our universe, before the creation of the Higgs field, which happened a trillionth of a second after the Big Bang, the weak nuclear force and electromagnetism were the same force, called the electroweak force. Then the Higgs boson came into existence and with the Higgs field, and the interaction of the W and Z bosons with this Higgs field caused them to not be able to travel as far. The W and Z bosons are what are responsible for the weak nuclear force. And photons, which are responsible for electromagnetism, did not interact with this new field and therefore could travel indefinitely, and that separated these two forces out. Now, the Higgs field is made up of Higgs bosons, like water molecules in a lake. And the Higgs boson is more well known than the Higgs field, and this is because you can't really detect the Higgs field, but you can detect the Higgs boson in a particle accelerator, and there was a lot of excitement around searching for and eventually detecting the Higgs boson. Now, its discovery has many exciting implications beyond just knowing where matter gets its inertial mass. The first of which is that Einstein's theory of general relativity tells us that a field that is uniform and made up of particles with zero spin, both of which are true about the Higgs field, could be possibly responsible for the expansion of our universe. Now, this usually isn't ascribed to the Higgs field because it already has its job, but it shows these sorts of fields exist, and that's exciting. Another exciting implication is the fact that the observed mass of the Higgs boson, which is 125 billion electron volts, is theoretically unstable. Theoretically, it doesn't work. It doesn't work in our equations, and that basically shows there's a flaw in our model. That's exciting because it shows where to go. One possible way to fix this is something called supersymmetry. There are a lot of possible ways, but that's one of the more well-known ones, and this measurement of mass sort of has prompted the search for supersymmetry and other solutions. So, all in all, the discovery of the Higgs field and Higgs boson both show where inertial mass comes from and have many other exciting implications, making it a really important breakthrough.